Hello, welcome to the second lecture of week 4 of radio astronomy. We are continuing our discussion regarding signal processing and receivers. So we have covered a few things about basic signals and properties, what is a system, Fourier series and transform, continuous in discrete forms. We will teach today about Nyquist sampling and aliasing problem and different basic radiometer design, and finally end with heterodyne receivers. In last lecture, we established that understanding of the signal processing techniques and understanding of a system is very important in order to detect a radio signal from the sky. We also discussed that any periodic signals can be represented by Fourier series and Fourier transform. These are essential tools which we will require in the subject a bit more. Now, even to begin with observation study, we need to detect the source. So next few lectures, we will try to understand the theory behind such system, which mostly is LTI or linear time invariant systems. So our next concept we want to discuss is convolution and correlation. If you look into a linear time invariant system or LTI system, it is a system that produces output signal from any input signal subjected to the constraints of linearity and time invariance. If a system is LTI, then it provides predictability of the output signal and makes it easy to characterize the system and remove the effect of the system from the signal. Exactly or approximately is applicable to many important physical systems. The response yt of the system to an arbitrary input signal xt can be found directly using convolution yt equals to x times h t, where h is the system's impulse response and the star represents the convolution and not multiplication. Now the question comes, why convolution and what is convolution? The response of an LTI system is convolution because it follows linearity and time invariance. If you put these two properties together, you will arrive at a convolution formula. So a convolution can be two types, continuous and discrete, just like previous thing. You have an input signal and you have an output signal, where we say the H is the effect of the system, and so the output is basically nothing but X convolved with H. It can be like something like you have a dish, you have an antenna, and you're measuring the sky. So you have a sky which is coming in through your antenna. So you have a antenna have a far field radiation pattern or the beam, and so the signal which comes is convolved with the beam. So signal of the sky convolved with the beam is what we record finally. So that's one way you can understand the convolution. Convolution have different properties. Commutative property, where you can x1 signal convolved with x2 can also be similarly equal to x2 convolved with x1. Convolution of unitary unit steps can also be done. So distributive property, x1 convolved with x2 plus x3 is x1 convolved with x2 plus x1 convolved with x3. Associative property, you have the in particular order of association can be interchanged. Shifting property, x1 convolved with x2 is y, x1 convolved with x2 t minus t naught is y of t minus t naught. Similarly, x1 t minus t naught is also y t minus t naught. If you have both x1 and x2 are shifted by t naught and t1 respectively, then y shifted by t naught plus t1. Convolution with impulse, x1 can be convolved with a delta function, and so x1 convolved with a delta function of t minus t naught gives you x of t minus t naught. Limits of convolution. if two signals are convoluted, then the resulting convoluted signal has the following range: sum of lower limits to sum of the upper limits. The t extends from the sum of the lower limits to sum of the upper limits. Okay. So that is the one of the properties. Here we have two rectangles of unequal length to convolve with, which results in a trapezium. The range of the convoluted signal is sum of the lower limits to sum of the upper limits. So we have -1 to 2 and -2 to 2. The resultant limits become -3 to 4. The area under the convoluted signal is given by AY is equal to AX times AH, where AX is the area under the input signal and AH under the impulse response. So the area of the final output signal or convoluted signal is given by the product of the input signal and the impulse response both, and it can be proven. So you can prove that yt is given by x times h, and integrate the both sides, you get yt dt. So that gives you the ay, and here if you integrate, you have one integral for tau and one for the t. So one for the t is given by ah, and for the tau is given by the ax. To calculate discrete linear convolution, convolute two sequences, xn, which is ABC, a discrete sequence, and hn is a sequence of E, F, and G. So the convoluted output will be EA times EB plus FA, EC plus FB plus GA, FC plus GB plus GC. If any two sequences have m and mn numbers of samples respectively, then the resulting convoluted sequence will have m plus n minus 1 samples. Convolute to sequence xn 1, 2, 3 and hn minus 1, 2, 2. Convoluted output will be given as following the above formula. You basically get -1, 0, 3, 10 and 6. So xn contains 3 samples and hn contains also 3 samples. So according to the rule, the final convoluted sequence should be of 5 samples, which is the case. To calculate periodic or circular convolution, periodic convolution is valid for discrete Fourier transform. If two sequences of length m, n respectively are convoluted using circular convolution, then resulting sequence having max mn samples. Convolute to sequence xn 1, 2, 3 and hn -1, 2, 2 using circular convolution. Normal convoluted output will be given by -1, 0, 3, 10 and 6 following the rule as we discussed in the last slide. Here xn contains 3 samples and hn also contains 3 samples. So the final must have the maximum of 3 and 3, so 3 samples. Now to get a periodic convolution result, first 3 samples of the normal convolution is same next 2 samples are added to the first samples as shown below beside. So -1, 0, 3 and 10 and 6. So if basically for circular convolution, you return the first 3 and simply add the 4th one to the first one and 5th one to the second one in this process. So now to get periodic convolution result, you basically do this, the following thing, and so you finally have the periodic convolution result become 9, 6 and 3 with a length of 3, which is the case as per the rule. Correlation and autocorrelation. Correlation is a measure of similarity between two signals. General formula is given by x1 t integral of -∞ to +∞ of x1 t and x2 t minus tau dt. There are two types of correlation, autocorrelation and cross correlation. Of course, autocorrelation is defined as a correlation of a signal with itself. autocorrelation function is a measure of the similarity between a signal and its time delayed version. It is represented by R tau. R of tau 1, that is the same signal, is given by this xt into xt minus tau, which is the positive shift, and xt and xt plus tau, which is the negative shift. Tau is searching or scanning for delay parameter, if any. Properties of autocorrelation function of energy signal. Autocorrelation of R tau is equal to R star minus tau. Autocorrelation function of energy signal at the origin at t equal tau equal to 0 is equal to total energy of the signal itself, which is given by R0 is E minus infinity plus infinity integral of xt whole square modulus square dt. Yes. Now, autocorrelation function of a power signal is given by limit tau t tends to infinity 1 over t minus t by 2 to t by 2 and xt time convolved with xt minus tau dt. Sorry about this type. The property of autocorrelation function of the power signal. Autocorrelation exhibits conjugate symmetry. R at tau is R conjugate at minus tau. Autocorrelation function of power signal at the origin at tau equal to 0 is equal to total power of that particular signal, which is given by R0 is equal to rho. Energy spectral density ESD is defined as the x of f modulus square. This measures distribution of the signal energy over frequency. Using property of autocorrelation, E xt modulus xt square dt is equal to psi of xf df is equal to rf df. So major points to learn from this particular slide is energy spectral density measures signal energy distribution across the frequency. Autocorrelation function of an energy signal measures signal self-similarity versus delay, can be used for synchronization. A signal's autocorrelation and ESD are Fourier transform pairs. Cross-correlation function next is the measure of similarity between two different kinds of signal. Two different signals, not kinds of signals, sorry. Consider two signals x1t and x2t. The cross correlation of these two signals gives you R12 tau is given by R12 tau is equal to integral of minus infinity to plus infinity x1t into x2t minus tau dt. That is positive shift, and x1t plus tau into x2t, that is a negative shift. If signals are complex, then this second one should be the conjugate. Okay. Properties of cross-correlation function of energy and power signals. Autocorrelation exhibits conjugate symmetry. Cross-correlation is not commutative like convolution. Cross-correlation function corresponds to multiplication of spectrums of one signal to the complex conjugate spectrum of another signal. So R12 is basically x1 omega, Fourier transform x1 omega times x2 conjugate omega. This is called correlation theorem, also known as Wiener-Khinchin theorem. We will be using this quite well in the weeks to come. So the cross correlation function is nothing but the Fourier transform of the multiplication of the spectrum, also called the power spectrum, of both the signals Fourier transforms x1 omega and x2 conjugate of x2 omega. Let us see an example to make things a little bit easier. An LTI system's impulse response is ht given by 2 times delta t minus 1 and 3 times delta t minus 2, where delta t is a direct delta function. If the input to the system xt is an exponential function e to the power minus t for all values of t greater than or equal to 0, find the output yt at t equal to 2. So the output yt is obtained by convolving the input xt with the impulse response. Of course, so yt is xt convolved with ht, and that is given by x tau h tau t minus tau dt. Xt is nothing but e to the power minus t unit function, because it exists only in the t greater than 0. So this is represented easily by the unit function. So ht is also here. So then yt becomes this value. Substituting t equal to 2, you get y2 is equal to 4.73. Okay, so that should be clear. So again, I'm just going through. H is given, the impulse function is response is given, the input signal is also mentioned, which is xt e to the power minus t. It is only valid for t greater than or equal to 0. So we replace that condition with a unit function, unit step function, and then ht is there. So if we just replace them, you have a delta function. So delta function's property is that it responds is only to that particular period. So t equal to 1, it will respond nowhere else. So you have yt as all these things. So finally you put the yt value equal to 2, and you get y of 2 given by 4.73. That's your output signal at t equal to 2. Let's start our attention to something called sampling. Sampling is very important in real systems, real receiver systems. Sampling is a process which helps in conversion of an analog signal into a digital signal. This is important because data transmission in the form of digital signal offers various advantages like high efficiency, fast speed, low cost, low interference, low distortion, high security, etc., etc., etc. In context to radio astronomy, it provides us a way to store and analyze a signal. Hence, sampling is essential to improve the quality and transmission ability of signals over the communication channel. Sampling is performed using an electronic device / component called analog to digital converter, or ADC. ADC is a device which either samples a signal first and quantizes it into fixed level of voltages, or quantizes a signal first into fixed level of voltages and then discretizes it. ADC helps in converting continuous signal digital into digital format such that it can be stored or digitally processed with help of computational devices like FPGAs, PCs, etc. Nowadays GPU also is used. A continuous time signal can be represented in its samples and can be recovered back when sampling frequency f is greater than or equal to the twice of the highest frequency of the component message signal. This is a very powerful theorem. What it says is we are discretizing the signal. Okay. Now, is it possible to what should be the rate of discretization? At what frequency should we do it? This the sampling theorem, or Shannon-Nyquist sampling theorem, says that this rate of the sampling should be greater than twice the highest frequency available in the signal itself. Let's consider what it is. So let's consider a continuous time signal x of t. Let's say the spectrum of xt has a bandwidth of fm hertz, f of sub m hertz. That means spectrum of xt is 0 for omega greater than omega m. So omega greater than omega m, it is response is 0. So the highest frequency is bandwidth of fm, right? Then the sample input signal x of t can be obtained by multiplying xt with an impulse train delta t of period t. Then output will be a discrete signal called sample signal and is represented by yt in the diagrams. So you have a constant signal, a continuous signal xt, and now you are trying to discretize it. So you have impulse train of delta t coming from the other end, and then you multiply them and you finally get yt from the other side. So here you can observe that the sample signal takes period of the impulse. The process of sampling can be explained by the following mathematical expression. Yt is a sample signal is xt times delta t. Trigonometric Fourier series representation of t is given by delta t is equal to a0 summation over n equal to 1 to infinity an cosine n omega st plus bn sine n omega st. This gives delta t is equal to 1 over t sub s, and then summation over n 2 over ts cosine n omega st plus 0. So you finally get the a0 value as 1 over ts, an is given by 2 over t, and bn's are all 0. If we substitute delta t, then finally we get yt is equal to given by this particular series 1 over ts x times t, x of t plus 2 cosine omega st xt, 2 cosine 2 omega st xt, and so on. Okay. Fourier transform of that expression gives us omega and y omega, capital Y omega is 1 over ts x of omega, x omega minus omega x omega plus omega s, x omega minus 2 omega s, and x omega plus 2 omega s, and so on and so forth. So it can be given by this particular summation series. So to reconstruct yt, you must recover input signal spectrum x omega from the sampled signal spectrum of y omega, which is possible when there is no overlapping between the cycles of y omega. So Nyquist rate for a band of frequency is the minimum sampling rate. Nyquist is the minimum sampling rate at which signal can be converted into samples and can be recovered back without distortion. So we are trying to discretize a signal. It's a continuous signal. We want to discretize it, and the discretization has to be done following a rate by which we can recover the entire signal and do not lose any information. That's the idea. However, we are discretizing. Okay, so discretizing meaning we are missing some timestamps in the signal, but we have to ensure that this loss of those timestamps do not cause any loss of information in the final signal. And if we do the sampling in a particular rate or above it, then we can recover the signal without any loss of information. That's what this Shannon-Nyquist sampling theorem is all about. So Nyquist rate is Fs greater than twice of Fm, where Fm is the maximum signal. So Nyquist interval is 1 over that. In case of a bandpass signal or signal with a frequency bandwidth, the spectrum of the bandpass signal x omega equal to 0 for the frequencies outside the range of f1, f2, where it is the upper and the lower limits. Okay. Now, if the frequency f1 is greater than 0 as per Nyquist rate, and there is no aliasing effect when fs is greater than twice f2. This leads to a couple of issues. Sampling rate is large in proportion with f2, and sample signal spectrum has spectral gaps. To overcome this, Nyquist rate theorem was modified to the following. The input signal xt can be converted into samples and can be recovered back without distortion when the sampling frequency fs is less than twice the maximum frequency but greater than twice the bandwidth of the signal itself. So where BW is the bandwidth of the signal. This is valid, and it is possible to up convert and down convert frequencies. This is the change or modification in the original Nyquist rate theorem for a band limited signal. Sampling in DFT, an analogy. Earlier it was noted that sampling is necessary for DFT such that the signal DFT is discrete Fourier transform, such that the signal can be reconstituted from its DFT. Sampling theorem says the complete reconstruction is possible if the sampling frequency is greater than or equal to twice the bandwidth. Similarly, if we take n samples per period of the continuous frequency, periodic signal XF with period 1, we expect the spectrum can be reconstructed if n is greater than the duration of the time signal x of n. Recall, sampling operation is equivalent to multiplication by a train of impulses. Hence, the sampling at intervals of 1 over n effectively forms the new spectrum given by x tilde f of this. The impulse train in discrete form can be written as summation over delta n minus r of n, Rn. The convolution theorem shows that inverse discrete time Fourier transform x tilde n of the sample spectrum x tilde f is the convolution of the original signal xn by a periodic train of unit samples. So x tilde n is nothing but a convolution of the original signal xn with this impulse train. Okay. The relationship between xn and x tilde n shows the signal x tilde n is a periodic with period of n. It is said that to be a time aliased version of xn by analogy with the frequency aliasing formula. Thus, if the sampling is improper, then aliasing will be present in both frequency as well as time domain. So, if sampling is not done properly in time domain or in frequency domain, there will be an effect called aliasing, which will be present in both frequency and the time domain as well. So, takeaway message is that if you want to discretize the signal, why do discretize it? To convert it from the analog to the digital form, which makes life easier. We can transport the signal quickly, we can store the signal properly, etc., without loss of the signal, without other interferences, etc. However, when you are doing a continuous signal to a discretized signal, you should also make sure that it is sampled in a particular rate that is given by the Shannon-Nyquist sampling theorem. For a continuous signal, there is no problem, but for a band limited signal, which is a start and the end frequency, so it has a bandwidth BW, there the sampling rate becomes lesser than the highest frequency present in the band, but greater than the bandwidth of the signal itself, twice the bandwidth of the signal itself. This is all which we have learned. If you do not sample at that rate, you face aliasing. So examples, which of the following is correct statement about sampling theorem? Nyquist rate causes aliasing. Sampling theorem for signal with a bandwidth of fs less than or equal to twice BW. Aliasing is can be avoided by following the sampling theorem and none of the above. So C is the true. Aliasing can be avoided by following sampling theorem. Second question, if you have a signal bandwidth of 100 megahertz, choose the correct sampling rate out of the following. So the signal bandwidth is 100 megahertz. Choose the correct sampling rate: 150 megahertz, 220 megahertz, 180 megahertz, or 100 megahertz. So it should be at least twice the bandwidth. So it should be greater than or equal to 200 megahertz. Out of all the possible options, only B satisfies that condition. So answer is B. So now we shift from the sampling to something called noise. We have introduced noise a little bit. Let's keep discussing further in this particular lecture also. So far we have learned about signal. But in order to detect a signal, it has to be significantly higher than the noise in the system. Noise in the system can appear in multiple ways. That's what we are going to discuss now. So, unless we characterize the noise and be aware of all possible noise or interferences present in the system or in the surrounding, it will be difficult to make a proper detection of the signal, particularly the signals if they're so weak like the radio astronomy signals. So noise is an unwanted signal, maybe intentional or random. There are different types of noise: thermal noise, short noise, partition noise, flicker noise, burst noise, transit time noise, etc. Most of the above stated noise are no dominant at higher frequencies except thermal noise. Characterizing and quantifying thermal noise is the most important for those who are working in radio astronomy instrumentation. So here on we will discuss about different types of noise, but keeping a focus on the thermal noise itself. Short noise in electronic circuits consists of random fluctuations of DC current, which is due to electric current being the flow of discrete charges or electrons. Partition noise, where current divides between two or more paths. Noise occurs as a result of random fluctuations that occur during this division. For this reason, a transistor will have more noise than the combined short noise from its two PN junctions. Flicker noise, also known as 1/f noise, very important characteristic noise. We will talk about it later when we talk about ionosphere, wave propagation, etc. But it's a very important thing to note, particularly regarding the electronic components and calibration of the gains of the electronic components. 1/f noise or flicker noise, or even called sometimes ping noise. The signal or process with a frequency spectrum that falls off steadily into higher frequencies with a ping spectrum. It occurs in almost all electronic devices and results from a variety of effects. So a white noise and a pink noise have two different characteristics. White noise typically is can be defined by a Gaussian random process, where you have a zero mean Gaussian or a Gaussian with a fixed mean, mu at mu zero and standard deviation variance of sigma square. Pink noise is a particular variety where the mu is not fixed. It varies with time. So there is no real mean for a long time if you track the signal for a long time. So that's one of the particular effects of flicker noise. Next is burst noise. Consists of sudden step-like transition between two or more discrete voltage or current levels, random and unpredictable at times. Can be removed easily by averaging of signal. The white noise also, if a noise has a characteristic of white noise, that basically means it's a fluctuation against zero mean. And if the mean is zero, or the mean is the signal itself without a positive DC bias, then averaging over multiple times reduces the noise particularly. Transit time noise, if the time taken by electrons to travel from emitter to collector in a transistor becomes comparable to the period of the signal being amplified, that is at frequencies above VHF and beyond, the transit time effect takes place and noise input impedance of transistor decreases. From the frequency at which this effect becomes significant, it increases with frequency and quickly dominates other sources of noise. Now, how do we characterize this thermal noise? So let's go back a little bit and start from the place where we left the discussion of the black body and the Rayleigh-Jeans law. Let's consider a resistor, a passive electronic component that absorbs electrical power and converts that power into heat. simply Joule heating. Okay. As per the black body laws, the temperature T greater than 0 Kelvin generates some electromagnetic radiation, aka electrical noise. The frequency spectrum of this noise depends only on the temperature of an ideal resistor and is independent of the material of the resistor itself. The derivation of the electrical power per unit bandwidth P nu generated by a current in the resistor. So at low frequency, H nu very less than kT, and Rayleigh-Jeans approximation is accurate. Recall Rayleigh-Jeans derivation of B nu starts with a large cube of side of length greater than lambda, containing standing waves of thermal radiation. Consider two identical resistors at temperature T connected by a lossless transmission line as a pair of parallel wires of length a much larger than the longest wavelength of interest. Standing waves on the line must satisfy A equals to n lambda over 2, where n is 1, 2, 3, 4, so on. Where lambda is the wavelength, electrical signals do not travel at exactly the speed of light on a transmission line, but at some slightly lower velocity than that. Okay. So the setup is like this. There is two resistors connected by two wires. There is lossless transmission line. Okay. And that is kept like in this particular diagram. For A, which is the length of the transmission line, is very larger than the lambda of the highest wavelength possible. The number of modes per unit frequency is given by n nu is equal to twice A over frequency. The classical Boltzmann law says that each mode has an average energy of kT in the equilibrium. So the average energy per unit frequency E nu in the transmission line is given by E nu is equal to n nu k times t, that gives you 2 akt over nu. This energy takes a time t, which is a over velocity, to flow from one end of the transmission line to the other. So the classical power energy per unit time per unit frequency flowing on the transmission line is given by P nu of energy over delta t, which is the time it takes. That is given by twice kt. However, P nu is also independent of the velocity. So here the P nu is given by 2 kt. If the noise power has a bandwidth of B, then the total power, the bandwidth over which the noise is measured is called B, then the total power of the noise power density becomes equals to P is equals to twice kt times B. So noise power is determined by only and only the temperature. Okay, that gives rise to this thermal noise effectively, and the bandwidth of B. In radio astronomy, we are interested in learning about nature of signal from the sky, for which we use radio antenna specifically. Antenna temperature, you remember, that is given in terms of this the flux density. So you remember that lecture where we consider S is K times delta TA, where delta TA is nothing but the change in antenna temperature when the source of interest was within the field of view minus the antenna temperature when the source of interest was not in the field of view. So it's the background subtracted. So the K times K is the Boltzmann constant, delta TA is the differential antenna temperature, off source and on source minus off source over the effective area. So that gives you delta TA. S is the flux density of the source itself. Now correspondingly, the effective antenna temperature is also given over here, omega A over omega S, where omega S is the angular size of the source, and omega Ts is that source temperature. Sorry, it's not antenna temperature, and AE is the effective collecting area of the antenna itself, and omega A is the antenna beam width. Okay. So now, if antenna is detecting a change in temperature, then that will show as a deflection in the received signal. This deflection does not come purely from only the sky. So we are definitely looking for signals from the sky, but in the path, the signal itself collects a lot of corruptions due to the wave propagation through the atmosphere, etc. In the neighborhood, the antenna is also collecting a lot of interfering signals, etc. from the neighborhood, okay, which are propagating in the same bandwidth as the signal itself. So, if you are observing a deflection in the voltage or the power received, then we can define a quantity called signal to noise ratio, which will quantify how much signal strength, when compared to the background noise. So signal over the noise is what we have to maximize. This SNR, higher the SNR, the more confident we will be about detection of the signal. Okay, the more significant the signal detection will be. So we have seen that the signal is already weak, and because of the propagation through medium, it weakens further. Not only it weakens, but also it gathers other noises, other interferences, which makes the signal to noise even further reduced. So effort should be taken to improve or increase the signal to noise ratio. So when we detect the signal, the received signal will undergo different steps like amplification, filtering, etc., etc. This post-processing of the signal might contribute also to the noise. Thus, there is a fear that it might reduce signal to noise to such a level that signal will not be recognized. For this reason, a quantity called as noise figure was defined, which will provide the idea about how much noise is being contributed by the system itself. So the signal is coming from the sky. It gets detected by the antenna and then pushed through the other front end and back end system of electronics, which amplifies, filters the thing, mixes signal, square law detector is there, etc., etc. There are a lot of other electronics is there. While passing through these different stages of electronics, the signal also suffers attenuation, suffers a lot of other things, like contribution of the noise in the signal increases because of system itself. So the desirable thing is the system itself should be at a lower temperature, lower noise temperature. Sometimes that is ensured by putting in the system inside the cryogenic devices, because thermal noise, the major thing is the system noise itself, and if thermal temperature is maintained at a lower ambient temperature, then the system noise contribution can be lowered. Other thing is that we choose by default low noise electronic devices like low noise amplifiers. So in radio astronomy, low noise amplifier is the by default term. The RF amplifier is used only after the low noise amplifier is initially put in place. So noise figure of each individual component of the electronics matters a lot. So designing a proper adequate receiver requires the specification of individual components also has to be checked. Okay, so one such thing is noise figure, which we discussed before also, and we are again discussing now. So amplifier, of course, is a term that amplifies a signal. Amplification is required. Suppose our antenna is very far away in the field, and we are bringing the signal back to our location of where the computers are placed through coax cable or any other cables, or even OFC, optical fiber cable. There will be some attenuation because of the length. So the before sending the signal through the cable, the typical thing is to amplify the signal. So amplification itself comes with a cost, that there could be some noise induced by the electronic component itself. So first thing is choosing the low noise amplifier is required. Second thing is choosing a cascade of such amplifiers to give it a more higher gain. Okay, so we'll talk about it now. So say xt is the input signal to this amplifier, and yt is output signal, and the signal to noise when the beginning is SNR I, and leaving the output is SNR O, or output. And this particular amplifier is a LTI system having gain G and noise figure of N sub A. So the noise figure, noise NA, sorry, the noise figure of this simple system is SNR I over SNR O. That comes down finally to 1 plus NA over G times NI, where NI is the noise present in the input signal itself. In terms of noise temperature, noise power is defined as N is proportional to T. Considering that the environment temperature is T naught, if there is a detection, this will cause the noise temperature to increase in the system. Then the noise figure of the system can be defined as F, which is given by noise temperature at the output over at the input. So T naught plus TE is the noise temperature at the output, and T naught is the one at the input. So TE is the device contribution to the noise temperature overall. So 1 plus TE over T naught is the total noise figure of the system itself. As I said, a cascade of amplifiers are required sometimes to provide a higher gain. So for a cascade system, the noise figure kind of varies like this. It is not just simple sum, but following this kind of a thing, you can understand that the total noise figure of this system, where you have a cascaded components of 1, 2, 3, etc. up to n, there which has a noise figure of F1, T1, G1, F2, T2, G2, etc. etc. So Fi, Ti, and Gi are the three different components of this individual cascaded sub components. Then the total noise factor is equal to F1 plus F2 minus 1 G1 plus F3 minus 1 G1 G2, and like this. So for the nth component is Fn minus 1 G1 G2 up to Gn. Similarly, the cascaded system temperature, equivalent noise temperature, is given by T1 plus T2 over G1 plus T3 over G1 G2, and then for the nth component Tn over G1 G2 up to Gn minus 1. This is very important to know while designing a proper radio receiver. Let us take a look at the noise since we're talking about the noise temperature, let's take a look at the noise temperature or the system temperature in addition with the antenna itself. So system temperature refers to the effective temperature of the entire system, including the antenna and associated components that receive or transmit electromagnetic signals. It is a critical factor to determining the sensitivity of the signal to noise ratio of a system. See, sensitivity of a system is very important because we need to understand, we have to build a system which is sensitive to a particular signal. If the signal is already faint, the system has to be super sensitive. And supposedly let's take an example. Like if I am looking at the sun, for that the telescope which I will be building and the electronics which are required will be of much relaxed specification then supposedly I am looking at a distant star or a galaxy which is millions and millions of light years away. Sun is brighter and nearby, whereas this particular faint galaxy is far away, and so I have to build a much more sensitive system. So that this budget of the system temperature is very important to note in order to make the system more sensitive and build a correct system for a correct signal to be detected. Not every telescope is built for every possible signal. So the system temperature represents the equivalent temperature of an ideal noise source that would produce the same amount of noise power as the entire system. Contributing temperatures, contributing components to the system temperature are antenna itself, feed lines, receiver, transmitter electronics, etc. A fair culmination of the system temperature can be written as T6 is equal to TA, which is the antenna temperature, times TAP, the antenna physical temperature, multiplied by 1 over epsilon this E1, which is the antenna efficiency, minus 1, then TLP, which is the line physical temperature, multiplied by 1 by E2 minus 1, which is the line efficiency, and TR over E2, which is the TR is the receiver noise temperature. There are plenty of other terms, like the atmosphere creates one kind of noise. There are different noises for the surface. If there is a system, if the antenna is made up of reflector dishes, then the surface accuracy itself creates another kind of contribution to this thing. Various efficiency parameters, etc., etc. This is just one of the thing. We will see more detailed expressions in the coming lectures. This gives rise to 180 Kelvin. So the next thing to discuss about is the minimum detectable temperature, because we're talking about sensitivity. So what is the minimum temperature that a system can detect? That also gives a sense of what is the sensitivity of the given system. So let's say define that as delta T mean of a receiving system equal to the RMS noise of the system itself. So that is given by delta T mean is given by K prime T6 over delta F times T. That is also called delta T RMS. This is a radiometer equation which we will again see in the next week mostly, that how this is derived from the scratch. But what this says is that the minimum detectable temperature is a function of the system temperature, which is given in the previous one. More detailed can be also shared in the coming weeks. The essence will be the same, but there will be more components added to this system temperature explicitly. So system temperature is one of the reason it's in the numerator. So as system temperature rises, the delta T mean goes down, also rises. So the minimum detectable temperature rises. That means sensitivity deteriorates. So thesis has to be low to increase sensitivity. It is further lowered by delta F, which is the bandwidth of the receiver. So if the receiver bandwidth increases, the sensitivity increases because we are getting more samples of signals. Remember? So more the sample, all the fluctuating components of the noise, they will reduce, and only the mean component of the signal will get amplified. And T is the time. So the delta T mean, remember, has to be low for sensitivity to rise. So a system with delta T mean lower is considered to be higher in sensitivity. If it is high, then it is not that sensitive, because we can detect only the signals, the faintest signals, which are lesser, which are above this delta T mean, is only which we can detect by this system. So delta T mean has to be lower. That means system temperature has to be lower, because that is in the numerator, and delta F has to be larger to reduce delta T mean, and T, time of observation, also has to be larger to reduce this delta T mean, which makes sense because time samples and frequency samples will reduce the noise, at least the fluctuating components of the noise, which are just basically white noise components. Right. So in this case, the signal to noise ratio is then is by n delta TA over delta T mean. It's very vital. We will come back to this when we talk about single dish observing strategies and more. So before we proceed further, let's take a couple of examples. A receiving system has an antenna with total noise temperature of 50 Kelvin, a physical temperature of 300 Kelvin, and an efficiency of 99%. A transmission line at physical temperature of 300 Kelvin and an efficiency of 90%, and a receiver with the first three stages of all of 80 Kelvin noise temperature and 13 dB gain. Find the system temperature. So system temperature is nothing but the receiver. Okay, first we compute the receiver temperature. So it's a cascaded noise temperature formula we have used. So there are three stages. So total the temperature of the receiver is T1 plus T2 over G1 plus T3 over G1 G2. We have done it earlier in this in this particular slide. We did the same. So we use that same formula and come back with that. So all three are 80 and all the gains are 13 dB. So 13 dB gain is approximately linear scale is about 20. So 80 plus 80 by 20 plus 80 by 400 is equal to 84.2 Kelvin. You can try. Now the total system temperature is nothing but Tcs given by this is with Tcs by antenna temperature plus ambient temperature, physical temperature time 1 over E epsilon EAP 99% minus 1, then T of line temperature is given by this TLP is given by 300 again, and 1 over LP is E epsilon LP is 90%, and then TR. So we essentially follow this expression over here. This is Tcs. There's a typo. This should be Tcs, and this is T antenna, which is 50 Kelvin. TAP is 300 Kelvin, 1 over 0.99 minus 1, then 300 times 1 over 0.9 minus 1, and then 84.2 divided by 0.9. This gives rise to 180 Kelvin. So our next example is finding the noise power of a cascaded system output. Assume that the source noise temperature is Ts equal to 150 Kelvin. Also suppose that the cascade noise factor, gain and bandwidth are respectively 1.8 dB, 6 dB and 10 MHz. Find the available noise power at the output of the cascade. So going by the previous slides, if we go back to that slide where we discussed the cascade, given by this, and also the F noise figure is 1 plus Te over T naught. Let's see if we can solve this. So T cascade is given by F cascade minus 1 times T0, that is 232 Kelvin. The noise temperature of the overall system Tcs is given by T sub S T cas, that is 382 Kelvin. So then we have the noise power is K times total temperature times the bandwidth. Okay. So that will give rise to 1.38. This is the Kelvin, this is the Boltzmann constant plus 382, plus we have a gain of 6 dB, so that you convert into the linear scale, and also you have bandwidth of 10 megahertz. So 10 megahertz is 10 to 10 to the 10 to the 6. This is the bandwidth, and 10 to the power 0.06 is the gain. So total comes out to be minus 96.8 dBm. That's the answer. So we come to the last segment of our discussion, talking about it's all good. So we discussed about different techniques to do signal processing, signal analysis, different signals, different systems, Fourier transform, Fourier series, convolution, autocorrelation, cross correlation. We spoke about Nyquist sampling theorem, various tools, as well as the noise, discussion of noise, sensitivity, etc. Now let us combine them together and see how a basic radiometer, basic block of a radio telescope looks like. So looks like something similar. An antenna with a reflector to begin with. It may be antenna without a reflector also. Then a bandpass filter, because we do not want to see outside our band, because there will be a lot of more spurious signals coming from the outside the band. Then an integrator, which integrates the signal, which kind of lowers the noise level and increases the signal level. So SNR gets increases. So there are different bands. We will come that later also. But HF band, the high frequency band, is 3 megahertz to 30 megahertz. The VHF, a very high frequency, goes from 30 megahertz to 300 megahertz. UHF band, or ultra high frequency band, is 300 megahertz to 1000 megahertz. L band goes from 1 gigahertz to 2 gigahertz. S 2 to 4. C band is 4 to 8. X 8 to 12. KU band 12 to 18. K 18 to 27. KA, or K above, is 27 gigahertz to 40 gigahertz. Then V band 40 to 75, and W band 75 to 110 gigahertz. There are higher bands also, but this is what we will be concentrating on. Mostly, below 4 to 5 gigahertz. So different components which are used, different kinds of RF connectors will be used, because we have wires, adapters, attenuators, RF amplifiers, high gain amplifiers, low noise amplifiers, mixers, and filters that comprises this entire radiometers. RF connectors, specific type of removable mechanical coupling which is attached to an RF cable. There are several types of RF connectors, differentiate based on frequency of operation and size. N-type connectors works up to 11 gigahertz, big in size, and is for rugged use. SMA type connectors, sub-miniature version A, works up to 26.5 gigahertz. 2.92 mm connectors, which is similar to SMA connector, can go up to 40 gigahertz. RF adapters, it's a mechanical interconnect which connects or links different types of connectors. N-type male to female adapters, so if you have to join different cables, these are the adapters which is required. Attenuators, it is equivalent to resistors, however there is thoroughly characterized such that it provides a particular amount of power loss across it for a fixed band of frequency. So very, very accurate. It is used for isolating different components such that the operations are smooth. RF amplifier or high gain amplifier, it's a basically high gain amplifier, the signal. Low noise amplifier, as it signifies, the noise is kept low. Typically, after the end of soon after the collection of the thing from the antenna, there is a low noise amplifier, because you want to amplify the signal without adding much noise to the signal chain. Another set of components are extremely useful. They are called filters. As the name suggests, it filters out the signal based on the frequency. First one is low pass filter. It is only allows something signals below a particular frequency to pass, and anything above that should be stopped. High pass filter is just the reverse of the low pass filter. It passes, allows the higher frequencies to pass. The lower frequency are completely chucked out. A band pass filter is, as the name suggested, it allows the operations within the minimum and the maximum frequency as it is designed for. So it allows that pass band to pass and restricts the other frequencies outside the band to transfer. The reverse of the band pass is the band reject or a notch filter, which basically only rejects the signals between that frequency minimum to maximum to stop. Suppose you have a very strong line, a GSM signal line at 900 megahertz or so. You build a notch filter so that your telescope can operate in the same frequency without getting affected by that particular signal. Mixers, they have a very strong role when we talk about super heterodyne receivers. They mixes two signals. RF signal comes in and IF signal goes out of this. Its RF is radio frequency, it's an intermediate frequency, and what happens is a mixing with the LO signal or local oscillator. Okay, so if the IF signal is higher than the RF, that's up conversion. Down conversion is the reverse one. Lower sideband is the when LO is greater than the RF frequency, and when LO is lower, then it's called the upper sideband. So it mixes the two frequencies and causes a frequency shift at the end. So often we do a down conversion because if the frequencies are higher, we need down conversion to bring it to the lower passband, baseband signal. A typical radio telescope looks like this: a telescope, then with a front-end electronics. This is typically near the telescope itself. Then a long wire connection or OFC connecting to some back-end area where you kept another set of electronics, receiver back-end, and then the digital back-end at the end. These are made by LNAs mostly, and with some filter combinations. Similarly, at the back-end is also several other filter combinations, and some LNAs, RF amplifier, a local oscillator for the mixer, and the low-pass filter at the end. So as we know that the antenna temperature is temperature is given by P nu, which is the power per unit frequency over Kelvin, which is also linked with the effective area times the source flux over 2K. Now, so for a simple system like this, signal is collected. It's collected over a band limited region, so it's collected over the central frequency is nu RF, then the bandwidth is delta nu, so it is collected between nu RF minus delta nu by 2 to nu RF plus delta nu by 2. So typical radiometer consists of 4 stages: a low loss bandpass filter, a square low detector whose output voltage is square proportional to the square of its input voltages, so it squares the voltages in the input, and a signal integrator that smooths rapidly the fluctuating detector component. That's the integration, so time integration part mostly, and a voltmeter to detect the signal finally. So at the integration, you can see this is the sample after n 50 samples. You can see it's so much of a spread that the noise power is still high, and if you smooth over to 200 samples, you see that these fluctuations are going down, and so you're critically defining a mean signal more rapidly. So sigma t, which is the uncertainty in the signal, is given by the Ts, the system temperature, over this delta nu by tau, but also some gain variations. This is the full expression. We will take a little bit deeper look at the next week. The different kind of radiometers. This is a simple one in the first stage compared with the differential one, where there are 2 different feeds and you keep switching back and forth between the 2. It reduces a lot of these gain errors. So you can see the gain error coming from this simple radiometer is kind of dropped when you actually use a differential radiometer. More again on this in the next week. Finally, coming to something very important called super heterodyne receivers, where we actually the RF there's a provision of the we do not have to operate the entire signal chain at the simple radiometer. We have to operate the entire signal chain at the particular receiving frequency where the antenna is designed. But in this particular case, we can, in the second case of super heterodyne receivers, we can design our LO frequency such that the remaining part of the chain can operate in a single baseband frequency, no matter what kind of a receiver we can put in here. It has various advantages. Some advantages are following, that as we know, we cannot build a single system which covers a wide band because our scientific interests are varied. We do not want to restrict ourselves to a particular wavelength. So we need to build separate receivers at this stage of the antenna to observe separate things. However, for all of those, the backend can be similar, extreme backend, because of this down conversion in it. It comes down to the same baseband frequency, and some of the systems are same for different other bands to be used. That's one advantage. There are several others which we will mention in the next slide. So let us understand what is heterodyne means basically. Okay, this is like another design of the same. Suppose example, we have a RF signal at 5 gigahertz with a bandwidth of 100 megahertz. Now mixing signal nu1 and nu2 will result in the heterodyne frequency of nu1 plus minus nu2. If nu1 is received frequency or nu RF with a bandwidth of B, which we are mixing with a signal with frequency nu2 or nu LO, local oscillator, then the shifted frequency will look like nu RF plus minus B by 2 minus nu LO and nu RF plus minus B by 2 plus nu LO, minus nu LO and plus nu LO. This means heterodyning a bandwidth signal doesn't change its characteristics, but it just shifts the frequency up and down. So typically we take the lower value. We don't allow the higher value because typically a super heterodyne receiver is followed by a low pass filter actually. The different stages, there's a RF gain stage and RF line filtering stage. RF gain stage amplifies signal power to a sufficient level such that the faithful mixing can be performed. Generally, there are low noise amplifier is kept first to make overall noise figure of system to be low or minimum. RF line filtering, in between RF filtering line, a BPF or a band pass filter or a combination of LPF and HPF are used for a band selectivity. It is important as amplifiers are not always narrow band, so they might amplify the signals out of our band of interest. So filtering will allow us to remove unwanted frequency. Mixer and LO. So LO is one of the most vital part of the super heterodyne receiver. Generally, LOs are near pure sine and cosine wave, such that it will have a single frequency in the spectrum. Impure LO have harmonics resulting in various impurities. IF line filter. Now, in case of a receiver which we are interested in the right, after mixing an LPF is used to cut off the higher frequencies. So our idea is to down convert. If you have to up convert, we will have a high pass filter which will allow the higher frequency to go through, that is nu RF plus LO and stoppage of the lower frequency. But in this particular case, we are interested in the down conversion, so we use a low pass filter which will allow the nu RF plus minus nu LO to pass, but stop this higher frequency to pass. IF amplifier, then after that band pass, some attenuation will be anyway introduced. So you need another IF amplifier at the end to amplify the signal to retain its characteristics. So that completes the discussion of the super heterodyne receiver. Again, the advantage is you can keep some part of the signal chain constant even if you use different kind of front end for collecting different signals at different wavelength band. There are other advantages of doing down converted signal to lower frequency that we'll discuss later. Sometimes up conversion is also required. It depends on the nature of the surrounding. If you have too much of interferences in a particular baseband, you can also up convert and then down convert finally. So different combination of up converter and down converter can be used in a signal chain as well. It is not uncommon. The last topic of today's lecture is the RF budget and power budget, link budget, etc. So we have to make a budget of how much is the power loss attenuation the signal will suffer from its very first tapping in the antenna till it finally gets recorded in digitally. Okay, and that budget is very, very important. For example, I just use the example to demonstrate that a radio antenna receives a power of minus 100 dBm, which is then amplified by an LNA having a gain of 20 dB. Then it is transported to the base station at 400 meters using an RF cable with attenuation losses of 0.25 dB per meter losses. Assuming the receiver requires a power of minus 40 dBm for faithful detection, then calculate the required gain. So the receiver requires certain input power to do its job properly. There is minus 40 dBm. And the antenna receives the power at minus 100 dBm. So the best the possibility would be maximum of 60 dB loss. So the gain required by the Bx. Then by the above formula we have minus 40 dBm is equal to minus 100 dBm minus 0.25 into 400 dB plus 220 plus x dB. So if you do all this thing, x comes out to be 140 dB additional amplification required at the antenna stage before it is getting transported over the cable. Okay. So we have come to the end of this this week's lecture. Again, a disclaimer: we have not generated all the material by ourselves. We have referred to several books, lectures available, and so we have referencing them here and acknowledging that contribution. Thanks for joining. See you next week in the class. Thanks.